now what we're going to do is connect work and kinetic energy. And it's sort of, we've kind of been doing it, right? I've kind of been calculating work and talking about it, speeding things up. But now we want to do it a little more carefully with a theorem. We love theorems. Work, kinetic energy theorem. You got to decide formally how are these two things connected to each other. Okay. So, and we got to get into systems, kind of like we did with momentum. Okay. External work. We got to talk about what external work means on a system. External on a system equals change in kinetic energy of the system. Of the system, not of the plants in my office. It's like related to the problem. So if we're going to write that, there actually is a plant. If we're going to write that as a formula, right like this: the work that we've been talking about. F dot dr, the system pushing something, we'll put an ext there. Make it clear, we mean something pushing. So before, like the cart, I didn't get the cart out. When we pushed the cart was a system, and I pushed it with my hand. Equals delta K, the change in kinetic energy of the system. So that's basically the work kinetic energy. Everything we did with work, we were doing this. We were speeding things up. We were pushing on things to speed them up. Okay? You can also write it there. So when we get into changes, there's a lot of way to write them. I'll do it more next week or Thursday on when we get to potential energy. Oh, my watch is here. Will there be class the Tuesday before Thanksgiving? Of course. Why would there not be class? Can you explain that tension equation again? Sorry, I didn't have this on and I missed it. Why is dr related to tangential velocity on angular? Because it is in the tangential direction. The direction this thing goes, it's always moving tangentially. It's never moving radially. Okay, sorry, I'm not catching. So, this you could also write, if you wanted to, as K final minus K initial. So when we get to conservation of energy on Thursday, we'll spend a lot of time talking about how to think about differences, how to keep them straight. So that's just your first look at it. Okay, so here we're going to push the cart. Here we go. So the cart here. We're going to do the whole thing. So we've got a cart like this that rolls on the surface. Okay, so the cart is the system. So you got to decide what's in the system. Is it the table? The table in the cart, the hand? Right now we're saying it's just the cart. So I'll put a dotted line around it. Just the cart. And it helps. It's a frictionless surface, frictionless cart, so it doesn't really interact with the table. So U equals 0. Okay, no friction. Perfect wheels. Now I'm going to have a hand that's going to push it. Like that. Hand applies, and it must be external, because I'm not part of the system. External force. So force F push. So what's going to happen? Here's the hand. Wait, let's go the same way. There we go. I don't want to confuse you. All right, here's the system. Here's the hand. I push. It speeds up. I pushed from one position to another position, and it sped up. So let's see if the signs make sense. It went faster. Okay. So the work external. We're not going to recalculate these because we basically just did it a bunch of times. Is the external work positive or negative? Let's think about the vectors. I'm going to push it from here to this lost little chain that somebody hasn't picked up yet. Okay? I'm going to push from there to there. Which way is the displacement vector, the delta R? It's that way. I'm going from here to here. I can draw it on here. There's the displacement vector. And here's the force. Same direction, right? So F dot R, so F is parallel to R, so it's positive. Okay? If the work external is positive, then what is the change in the kinetic energy of the system? Positive. That's an equation sign. That means these must be same. So what does that mean? Well, that means this is positive, which basically means K final is greater than K initial. What does K final greater than K initial mean? Well, the mass didn't change. Did 1/2 change? 1/2 didn't change, so the velocity changed. The velocity increased. 1/2 mv squared. If the fountain was bigger than the initial, then it sped up. And sure enough, there it is, speeding up. So as I push it, it gains kinetic energy. That's really all this is saying. The only tricky thing about it is it's keeping up with external, what the system is. And it's mostly intuitive, but in some problems, it's not as intuitive. For a rotational version, I don't have one here, but if I had a disk and I pushed it, right, the disk would have 0 omega at first, 0 angular acceleration. If I push it, I'd apply a torque. Okay, I would apply a torque to the disk, and what would it do? The disk would speed up. And the disk would gain kinetic energy. Oh my God, we could do all this rotational, but here's why we don't. You ready for this? Let's do equivalent things. Work for translational is the integral of f dot dr. What would it be for rotational? As I apply a torque to the disk, force is torque. Torque dot, what do we go through? A theta, d theta. Oh my God, I don't want to get you guys through what d theta vector means, so we're not going to do that. Let's just keep it translational. Because then you have to acknowledge that all those torques maybe were rotational things were vectors, which they are. We didn't get into. So we're just going to keep things mostly translational when it comes to this motion. But you'll see on the homework, we'll try to make some rotational stuff in. Okay. Okay. So now here's something about signs of kinetic energy and work.